Hello, everyone. This is part 2 of the truss joist tension design. And we're going to go over this problem here to demonstrate of what we have learned from part 1. So the problem statement reads, a roof system consists of a worn type roof truss as showing in the figure below. The trusses are spaced 25 feet apart. So imagine this a truss joist of ceilings. I'm sure you've seen them in warehouses and so forth. They are spaced 25 feet apart. The length of the truss as a structure system itself is 36 feet. Okay. Loads are passed on the truss through the purlins that you can see in the top. Design the bottom chord members consisting of the two angle sections separated by 3/8 of an inch gasked plates. Assume one line of two 3/4 diameter bolts spaced 3 inch at each joint. Use the area steel classification as A572 steel. As you can see, we have 5 types of loads. Now, I want to remind you of the load combinations. We went over the load combination in part 1, and according to that, you should use your case. Now we have dead load of 10 PSF. That the dead load works for the deck, roofing, and insulation, but not necessarily the weight of the truss itself. It's included in the dead load, so we have to consider that. And then we have a snow load, roof, and wind, and so forth. So following the procedure we went over, let's jump right in the solution. First, to start with, we need to identify the computation of the load or the load combination. Like I said, because your dead load is 10 PSF, we added 20% worth of weight of the truss to make it 12 PSF, as you see here. So then, if we look at the load combination, we took case number I believe 2 and 3, if I go back to them. So we have a snow. We don't have life load, but so we don't need to. So we're not going to take case 1. We're not going to take case 2. We have dead load. We have a snow. We have wind. So case 3 is 1. Case 4, we have dead load, wind, and we have snow. So case 4 works, and the rest don't. So then 1.2 dead load plus 1.6 snow plus 0.5 wind. Plug in chug. It gives us a 68.8 PSF. Then the second case is 1.2 dead load plus wind plus 0.5 snow, and it gives us 44.9. Now, the higher controls, because we always want to be conservative, right? We take the highest load, and this is what we're going to take. This is the load factor, remember. So then, what is the tributary area? The tributary area is 36 by 25, because they are spaced 25 for a length of 36. We have 600. Then we multiply 900. So we multiply the 900 by the controlled load factor, which is 6.8, and that gives me 61,920 pounds or 61.92 kips. Now, if you look here, we have 1, 2, 3, 4, 5, 6, 7 purlins. We have 5 interior and 2 exterior. Now, typically in a tributary area, imagine the tributary area of a purlin. We went over this in the wood design class, if you guys remember. the exterior takes half and half, right? So we are concerning just on this half, which means this load here takes half of the load. The same goes for this, the other end. While the interior take the entire load, right? Each one of them take the full amount of load. So then if we divide the 61.9 kips by 6, because the 5 interior purlins plus 2 exterior half, so the 2 exterior add up to a 1. Imagine those are the 5 that carry all the load. So we have 10.32 times 5, because there are 5, right? Plus we have half. If 10.32 is divided by 2, it gives me 5.6 because we are concerning on just this half. So then we have plus 10.32, right? This comes from 5.16 times 2. So then the total of this here gives me this, the 61.92. So then we divide them by 6. Why? Because we have 5 interior plus half and half exterior, which total up to 1. That means 6 of the 10.32. It gives me this amount here. Then we divide by 2, and then gives me 5.16. So this is pretty much how we calculate the load at each purlins. Then that was the load computation and how we came up with these values. Now let's analyze the truss. Now, how many bays we have here? We have 1, 2, 3, 4, 5, 6 bays. This bay here, and this bay here, this bay here, this bay here, and those cords that belong to each bay are the weakest because they are in the middle. And because of that, we're going to look at this here. So then what do we have? We have, well, first here also, we have to find the value of the reactions. So basically by adding all these up and then divide them by 6, divide them by 2, we come up with 30.96, just like this step here. Right, the total of 61.62 divided by 2, it gives me the value of each reaction. Does that make sense? Just to reiterate, just to make sure that we got it. So we have all these loads, 1, 2, 3, 4, 5, 6, 7, with their values, add them up, and then divide them by 2. So we have the hinge and the roller reactions values are found. Now, what we're going to do, we're going to section it through here, just like the way we're showing AA section. We're going to section this part to analyze the interior or internal forces, which is represented by here, by this figure down here. So I'm going to stop and then continue on the next lecture due to the time constraint.